Thank you for that kind introduction. And I recognize I need to shorten that up. I should have given that a bit shorter. Sorry. So I'm going to start off with a land acknowledgement. That picture you see on the upper left there, I guess your upper right, sorry. That's the confluence of the Elbow River and the Bow River. Now in the Blackfoot language, the term for elbow is Mohinsits. And that's what they would call this meeting area, Mohinsits in the Blackfoot language. There's equivalent words for that and some in the blood time. But this is Treaty 7 territory. It's traditional ancestor territory of the Blackfoot Confederacy, which is the Kanipa County Siksika, as well as Tsuut'ina Nation and Stoney Nakoda First Nation. And of course, it's also home to the Métis Nation of Alberta Region 3 and within the historical Northwest Métis homeland. So it's an interesting part to start from because it also then starts to think about time. Indigenous people have been in Alberta for at least 10,000 years. And in fact, this is a stone artifact, which actually shows that Indigenous people did do mining back then. And there was a big trading route. And the spearhead is carbon dated some 10,000 years ago. It's also that equivalent to about 500 generations. And if you think about it, I know you're probably a lot similar like me. I'm a third generation Canadian. My wife is here, Krista. She's actually a 15th century generation Canadian. Her ancestors came to settled from the French settlers on Atlantic Canada in the Cape Breton area in Nova Scotia. So that's a long time, but it's nowhere near 500 generations. And the point I wanted to be is that time becomes incredibly important. So one of the first things I wanted to land on with you as we talked about a land acknowledgement and then switch to what I would argue is land transition, right? Is that when you're transitioning land, you need to think about temporal scale. Time is important, getting on the same page as that. So here's a framework that we stole, the International Network for Acid Prevention, INAP, when we wrote a global cover system design guidance document published in 2017. And we stole from the Canadian Dam Association a thought process and framework for thinking about temporal scale and time. Right? So on the vertical axis in the middle there is the level of effort that you put towards closure planning as you go through the mine life cycle, which you see it on the bottom of the axis. And you'll see different terminology and adaptive management, proactive, reactive. But the point I wanted to make is we often use these subjective terms, short term, immediate term, long term, all of those kinds of terms, but they're subjective. And what you think is short term might be something that I think is long term and vice versa. So we know that's important, and we know it comes in throughout our industry. If you're involved with development of a resource and development of a project, you maybe have contributed to an NI 43-101. This is the instrument, the tool that allows us to define resources and reserves and use these modifying factors. It's the mining rule, the application of law and policy that allows us to develop our projects. And, if you haven't guessed now, we measure over time the discounted cash flow of the value of the asset as we move from exploration to resource to economic assessment, reserve, and then into production. So there, time is important. Temporal scale is really incredibly important. Again, even if I was thinking about a lot of us are design engineers, we do a lot of design. Well, there's design life. What's your design life? Your life expectancy of your item that you're designing. And what's your assessment period of what you're actually going to go and understand risk? Time is incredibly important. If I was in the mining industry and I was thinking of at a mine site and I'm worrying about production and getting that rock out in the dock and being able to build my mine rock stockpiles and tailings storage facilities, it's planning and operations. Life of mine would have a different context for time if I was in the closure planning space. Right? I'm a closure planning practitioner. I'm thinking of the line life cycle. So automatically, if I have used these subjective terms and I haven't defined them for a particular project and with the people I'm working with, when I'm on a different temporal scale, I've got a different risk profile. And therefore, one of the key messages I want to bring across is usually when there's a disagreement about design, one of the first cases to look for is there's misalignment on temporal scale. What you think is important over time may be different than I think is important, because I'm going to tell you, I'm going to solve that problem later, or vice versa. So temporal scale and getting in line with that is incredibly important. Now, one of the things that you may have heard of if you've been involved in the mining industry is these terms PAG, NAG, and TIL. So we know what TIL is, PAG, and NAG. Well, I was a haul truck driver as a summer student at a mine site in the north end of Vancouver. And all I knew is somebody would tell like truck 1859, take it to the PAG pile, the NAG pile, the TIL pile. I had no idea. All I knew was I was making a lot of money as a haul truck driver. Now, on the right-hand side is a Roman portal. And there's documented evidence from the mid-1500s of acid rock drainage. Right, that's familiar iron staining, that iron hydroxide that you see that might be in the water. As the water that's at a lower pH then becomes oxidized as oxygen, the pH ranges, and then the iron sulfides, iron hydroxide, sorry, starts to drop out. So that's that balance of the potentially acid-generated material. Essentially, it's just accounting, right? We're balancing how much sulfidic material, the acidity we generate, against how much neutralizing capacity is available in the water. And when there's 2 to 3 more times alkaline material, we label it as just non-acid generated. When there's less than that, then it's potentially acid generated. When it all comes together, it manifests itself as acid rock drainage or metal leaching and acid rock drainage. And that's what we saw in the picture there, metal leaching and acid rock drainage. That's the issue that we most often have to deal with on a long temporal scale within the mining industry. Now, you can have all kinds of metal leaching acid rock drainage, a wide range of pH conditions from basic to acidic, and a wide range of concentrations of metalloids. The bottom axis is sulfate, the top axis is a bunch of metals and metalloids, right? It's a huge area. More acidic acid rock drainage, called neutral rod drainage, or might just have salinity in it, some sulfates and other salts, right? It's all arises from metal leaching acid rock drainage. Because what are we doing? We're taking something out of the ground and placing it in the first imbalance it's going to face, a thermodynamic imbalance. It's chemically imbalanced. We're providing oxygen to it, and it's going to move and want to move to a lower energy state. In addition, we're putting it above ground. So the other driving force, gravity, it's going to want to drive towards a lower energy state. So most of what I'm going to talk to you about today is these two things that are working against us: thermodynamic imbalance and gravitational imbalance, potential energy. Everything wants to move to a lower energy state. And so that's what the application of what I think I do most often is trying to balance this and understand it in the physical context of what the mine waste and the mine rock that actually putting the open. So, PAG, NAG. I didn't know what it was. I was working at the open pit, the Island Copper Mine, driving my haul truck around. And I was very fortunate. I was working with my older brother, Kevin, and I was living out for free. I was even better. I was a rich summer people. And he was doing a project where it was doing the south wall pushback. There was about a 1.5 kilometers or so, of about a 30 to 40, 50 meter rig of a slurry trench cutoff wall. And that's Rupert Inlet on the right-hand side, and the open pit, so they had to hold the water back. Kevin was the project manager, I was a summer student, I had to do a 4th-year project. So I said, this will be the easiest 4th-year project ever. I am just going to take all that data, write my 4th-year project, and be done. Okay? So eventually, just to tell the story of Island Copper Mine, they ended up flooding that open pit to manage the metal leaching and acid rock drainage. They flooded it by breaching the inlet, and now there's these beach dumps and North Catchment, South Catchment. Those are different mining stockpiles. So that's the closing plan for the Island Copper Mine with cover systems. But I went back and talked to Lee Barlow. I said, I've got the greatest project ever. He said, that does sound really neat, Mike, but you should go back and ask your brother if there's an acid rock drainage issue with that mindset. I said, I don't know what that is. I went back and talked with that, and he said, oh yeah, we have an acid rock drainage problem. So that's how I first got introduced to cover systems. How can we take that thermodynamic imbalance and that gravitational imbalance and put a cover system on to change the physics of the biogeochemical system in order to be able to have this system that stores water, releases it, maybe how to compact the till layer and all that sort of stuff. And in fact, the first time that I actually, after 2 weeks when I started on copper, I planted grass and seed and trees up on the North Lakes Road. I had no idea what it was. All I knew was such a young period. Now, that eventually led me to do my thesis at the Equity Silver Mine. Equity Silver Mine was a mine that at that time was owned by Placer Dome. So I was very fortunate. I had a really hands-on thesis. I was installing sensors. In fact, we were inventing sensors in order to manage and understand how that cover system was performing. And it had just been built. It was just finishing being built when I was starting to do my thesis. We're installing suction sensors and water content and weather stations and lysimeters and all kinds of things to say, how's the cover system doing? Now, my Aunt Kay on the left, my mom on the right, they're both very, very laboratory. And I would describe to my Aunt Kay gave me my love of animals and dogs, but she also had me appreciate how gardening. My wife's a very avid gardener as well. And I tell her like this super cool cover system, like hold on to water and we release back in the atmosphere, the water, the transpiration. She goes, that sounds really interesting, Mike. It actually sounds like gardening. I said, no, Auntie Kay. There's these water retention curves. And it's really cool because the clay holds onto the water and then become unsaturated. And then the gravel drains, right? And when I put that together, I've got these things called capillary breaks. So the gravel is drained, becomes a barrier for flow. I've got finer texture material on top that holds onto the water. It's a really neat thing. That's what the cover system we're testing here is. She goes, so that really sounds a lot like gardening. And I said, no. Like I've got this data. If you see the data, Annie K, like I drew all these, and I said, there, look at all the water that's being hang on over this coarse textured material here. It's drained, it's a barrier, it's really neat stuff. And she goes, Mike, that sounds like when I put the little pea gravel on the bottom of my pots. I put the topsoil on the top, and it hangs onto the water a little bit. I said, you're right, Annie K. And so that's why I dedicated my thesis to Annie K. And I said to her, who knows, my Aunt Kay, who knows what every good gardener knows, that finer texture material placed over the closer texture material is a photogenic system. So that's the next sort of key message, is that when there's disagreement about your design intent design, very often, just simply turn it off. Keep things as simple as possible, but no simpler, so you don't miss the little edges of complexity that you have for. So why unsaturated soil mechanics? This is what I grew up on, right? This is a chart from the Mine Environment Neutral Drainage Program. Sorry. Where we develop these different kind of cover systems. This is the cold regions cover system design guidance document. MEND report that we prepared for the federal government. And there's all kinds of different cover systems. Capillary break ones, reclamation ones, seasonally for frozen capillary break ones, store and release ones, reclamation, isolation, saturated. So I don't need to go through all of these cover systems. But I did want to share with you is that a few things that I believe that we all have in common, right? Is one of the first things is that they're all about land and water stewardship. They're that interface between the underlying material that the mine produces and the biosphere, right? They're what we need to be able to put in place and be in consistency, design with the landform, and so that I can actually understand the land use. Those are just disappeared. So it's land and water stewardship, land use, right? And in fact, if I thought about land use and just think about that, I'm going to come back to that later, that theme of the importance of land use. And it doesn't need to just be ecological restoration. There could be all sorts of things with respect to ecological restoration. It could be energy storage, energy generation, and all sorts of different things, some combination. What do they also have in common? On the far left-hand side, it's about water. So it's enhancing the near surface water holding capacity for plant water use. It's also about managing water, how much net percolation, how much goes down and leaches through, how much oxygen comes into the system, whether or not it's erosion. Have I created a system of high energy potential on a slope where the system wants to move to that low energy potential? And then I want to manage water and oxygen to minimize that net leaching gas creation. So I've got systems that are uncovered, lots of high water flow flowing through them, and I put a cover system in place in order to manage water and oxygen, and then pick up any remnant seepage from the base of the facility that might still have an adverse impact of the receiving environment. And I do collection, conveyance, storage, and treatment of that seepage so that I actually have water quality released to the environment. And as I said, they're unsaturated systems. Unsaturated, for all of you know, I didn't realize until I got into this, third year soil mechanics, when we were learning about compaction, that's unsaturated soil. Right? Some of the pores are filled with air, some with water, as opposed to a saturated system all filled with air. And finer texture material holds on to more water than coarser. And their performance is dominated by site-specific climate conditions. If I was designing a color system in Calgary, it would be completely different than if I was in the outback of Australia. Why? Because climate is different. If I was to design a line or a pond or a lagoon in those two different locations, arguably they might be about the same. Impact of clay, permeability, and all that kind of stuff. But because they're exposed to the atmosphere, their performance is dominated and influenced by site-specific. So when I think of cover systems, it's climate first. The lens that I look through is what's the possibility through climate first. And we use the Copenhagen climate classification system to conceptually describe climate before I start doing any fancy. What's the dominant season? Arid, temperate, tropical, cold. And then what's the seasonality of precipitation and rainfall? And before you know it, I've described the possibility of climate without even having to think about numerical modeling and without having to think of averages. And why do I not want to think about average? Because the average doesn't exist. None of us wore the clothes today based on what the average temperature was going to be today. You look at the forecast and you said, what does it tell you? It tells you the high and the low. It tells you the extremes. So with climate and that seasonality of precipitation and temperature, I can function with the extremes in the understanding as compared to the average is just a statistic that doesn't define it. All right, so unsaturated systems, cover systems, and landforms. Think climates first, and always think that cover systems are not caps, they're upside down lines. You don't want to fight nature, you want to work with nature. Their performance is strongly influenced by site-specific. All right, a little bit more story about me. I grew up in the mining industry. My dad and mom lived in Cuba, Philippines, different refineries in different places around the world. And I lived in the Canada and the Philippines. You can see there's a picture of my dad on the front page of the Northern Miner, for a mine site that was in the Philippines. You can see me here as part of the flotation here. They're doing a tour of the mill. And there's my sister and I. My sister's in flip-flops. I don't think you can get away with that anymore. But what I was really fortunate about is my brother also worked in mining. And he's gone on to a very long career. And he provides a lot of guidance and mentorship. But if I was to go back to the Island Copper Mine and tell a story of another fellow who was a big part of my life professionally, and that's Andy Robertson. I had a fortunate opportunity to interview him as part of the Landform Design podcast, Getting Closure. And in that podcast, I told Andy the story of when my brother was hosting my brother Kevin was hosting Andy at the Island Copper Mine. Andy was the rock mechanics slope engineer, the consultant for Island Copper Mine. And Kevin was the chief engineer. And he told his boss, Andy's coming to town. He's going to come and visit. And his boss said, well, don't let him near any more waste rock dumps because he's going to find more acid rock drainage. Stick to the rock mechanics. So Andy had a really good laugh about that. But Andy was a big part of my career. He was very supportive of me. I had a lot of long, great conversations with Andy over the years. So that's a super cool connection. And that would lead you to, on the right-hand side, where we'll focus. If you've ever done a failure modes and effects analysis, or a multiple counts analysis, which is now standard procedure in the mining industry. In fact, it's ingrained in some of the regulatory processes in many of the jurisdictions. Those were pioneered and with the vision of that law to bring them into our industry. So always talk about source pathway receptor, and you would recognize and say, hey, the cover systems and the treatment, that's a pathway and a receptor management mitigation. Right? Could we actually move up the chain and think about source control and apply these imbalances of thermodynamics and gravity to be able to manage tomorrow's risks today and not just rely on cover systems and treatment? Because our lived experiences is just this one example. This is from the Equity Silver Mine, and there's a great paper that's at the BC Metal Leaching and Acid Rock Creators Conference by Corey Binns and Mike Eases in 2018. And they report over 30 years of water treatment, collection of metalliferous and acid rock grains, and treating it in their high density sludge treatment system. Almost 1 million cubic meters of water treated over that 30 years of period. And initially, the 100-year net present value prediction of what they needed to have for financial assurance, the province of British Columbia, was $20 million. In 2017, some 30 years later, it was now $88 million. So there's increases on understanding the source term, with water coming from different places than they thought there might be, increases in line usage, increases in line costs, all calculated or on the way. And that's without the $1 to $2 million that were used to actually treat the water every single one of these 30 years. So our lived experience is, if we wait and try and solve the problem later, it might not actually be the best approach. Perhaps we should think about how do we actually solve it from a source code perspective. So the other next question is, why am I going to focus on mine rock stockpiles? A little bit about tailings storage, but why am I going to focus on mine rock stockpiles? It's because tailings storage facilities are finer texture material. The oxidation that results in that thermodynamic imbalance and makes it happen, that's a diffusion control system. It's surface dominated, right? It's going to diffuse through, it's going to oxidize sulfides, and have an advancing sulfide oxidation front. So you get harder and harder and harder to get oxygen into the tailings and oxidize that sulfide. It's self-limiting. On the other hand, mine rock stockpile is dominated by vector gas streams, entirely, as well as tailings and unsaturated soil mechanics. I have a material that's coarser textured, generally well graded. I place it over a large list, segregates. I got rubble zones down at the bottom, coarse and finer textures that are all over reposed, generally finer, coarser texture material at the bottom, finer at the top, but high airflow capacity. When I have a difference in temperature inside the facility, as compared to outside the facility, I have thermodynamic equilibrium. The warmer air is more buoyant, it will rise. It'll draw more gas in from the side. So I'm going to have this continuous resupply of oxygen for sulfide oxidation. If it's the other way around, where it's cooler inside than outside, if the temperature changes outside, that air will actually become less buoyant, it'll fall, and I'm going to draw more oxygen from the top. So I have this continuous resupply of oxygen, continuous sulfide oxidation, continuous generation of source. Of course, there's diffusion as well. There's lots of exposed surface areas, just in some way. So mine rock stockpiles contribute well over 75% of the acidity generated in the mine site. The fact that at Equity Silver Mine, in the 30 years of collection and water treatment data, almost 95% of the water they collected and treated is a result of the presence of mine rock stockpiles. It's not the tailings storage facility. In fact, where we often get metal leaching and acid rock drainage from tailings storage facilities, it's because the rock will lose to different elements, not actually from the tailings. Tailings need to drain down. We need to have all that oxidation products work through at a certain pore volume loss of 20, 30, 40, 50 meters from the top to the bottom, all the while picking up alkalinity. A good friend of mine, Peter Scott, and I wrote a paper at the Burkunda mine back in 2011 at the mine closure conference. At that site, 82% of the acidity that's generated that's been treated is from the mine rock stockpiles. The mine rock stockpiles represent the biggest risk in comparison to all other landforms and sources with respect to metallurgy and acid rock grade is because of that convective gas flow. So how the mine rock stockpile was built influences how to perform. It's how it was built, no different than anything else. Everything that you build is defined by how you build it. Coarse texture material, segregation from depth, thermodynamic in equilibrium, trying to actually, it's always trying to come to equilibrium, and then the material lets up, and I got the other one out, gravity, moving downwards. So these are structures with a high airflow capacity, consistent resupply of oxygen, continues, and then ongoing regeneration. And eventually it wets up, drains down, and I have metal leaching after drainage coming out of the base. So same thing happens for an open pit. The previous one I showed you was a balance type mine. So if I was on an open pit on flatter terrain, I get that same sort of action. I'll break out the two sort of conceptualizations. Here's my coarser and finer textured zones. Here's my rubble zone down at the bottom. There's the generally coarser to finer for that 30-meter length that I can see as conceptualized. Those things happen as well. So I end up this system where I go, I'm going to have non-engineered fill, and that's the definition over here. It's a geotechnical definition of steel. A low level of control and a high level of uncertainty of my outcomes. And then I'm going to build this complex cover system on top of everything. And I'm going to do water treatment. So I'm challenged with predicting the results with some confidence. Surface water, the recoverable, unrecoverable seepage ratio, meaning I've got water that's coming this way and that way. What percentage of that water do I need to pick up in my collection and treatment system to treat so that this unrecoverable seepage is okay to be released? That's a hard number to figure out. And then what's the quality of the water? So the best cover system is the one you don't need, but let me build on that. So I got this water treatment, that's a proven technology, high level of certainty. It's proven that there's new treatment technologies coming out, but basically, managing low pH water, putting alkalinity in line with it and dropping it out, and that's proven technology, right? But I would put to you, collection, conveyance, and storage of water is not proven. It's incredibly site specific. How hard or easy it is to pick up that seepage, entirely site specific. I'm going to pipe that water. I got a ditch. I don't want the ditch to leak. I'm going to pipe my seepage. We put it in a pipe. And now it's starting to fill up the sludge, and the sludge is what got the pipe. We got to put in. It goes on and on and on. Right? Is my pond big enough? I thought I designed it for 1 in 1,000. 1 in 1,000 happened, and then another 1 in 1,000. Getting this collection, conveyance, and storage is highly uncertain. Certainly wide range of outcomes. And how often do you build a pond well? So, same thing happens when I take this water treatment to my pits. So my open pit, flat terrain. Here's I'm depicting this deep ingress of oxygen, continuous resupply. It's warmer inside that facility than outside, so I'm gathering up gas, continuous resupply of oxygen. Same problem. I got to collect, convey, and store water. Lots of uncertainty there. And this is the tool that we look at, right? Decision making, there's a science behind it. I've got a high level of uncertainty and a low level of control. Automatically get out of fantasy world, you're in scenario. Right? A lot of different situations you got to take into, a lot of uncertainty, a lot of outcomes. We want to move towards adaptive management by imposing more control. But is the level of control that you're applying inside the footprint of the facility you constructed or outside? If it's outside, that's not really truly adaptive management. Because you're going to get into a locked-in position where you built a facility that the only way I can fix it is through collection, conveyance, and storage of water in a water treatment facility, and that we designed it right to the water. Now, the other part is I can reduce the uncertainty and have more prediction and monitoring. So what path do you actually want to go? Okay. Let's go down this first path here. Let's actually build my mine rock stockpile, recognizing that I've got run of mine material but I just have to apply a little bit of civil engineering to it. I'm going to reduce the lift height to reduce the segregation. I'm going to add a finer textured layer on top of each one of those layers. And what do finer textured layers do for us? They hang on to more water. When I got more water in something, the air permeability is low. When the air permeability is lower, I reduce the vertical airflow capacity. So now my airflow capacity with the same thermodynamic equilibrium can't reach far into my mine storage. I've created a large zone of suboxygen, no resupply of oxygen. And as water flows through, it actually has an opportunity to pick up more activity. Now I have an increased level of certainty, seepage collection ratios, simpler cover systems. So the cover system that I don't need is the one that's super complex. It's going to save the day. I can have a cover system that just actually is about erosion and landform stability and water. Not one that needs to be this magic thing. And I can manage the risk more effectively in cover system. Managing at the source. Here's an example of that. On the left, this is from a site in Turkey. On the left is a mine rock stockpile that's constructed and ducted. On the right-hand side is one that has source control. Right? So you can actually figure out what's the difference in cost to place them differently. And then you can say, Mike, that was a lot of arm waving with all that conceptualization. Well, I'm telling you, we can model it too. Here's that conventional mine rock stockpile. This is a coupled heat, water, gas model that allows us to predict the movement of gas and resupply of oxygen to that facility so I can calculate the acidity that's generated. Those red lines that are going back and forth are arrows, right? It's a 10-year simulation of mine rock placement and 15 extra years of sitting there operating, right? And what that ends up doing for us is it tells us that every time the temperature is warmer inside than outside, I get more gas in and flip it around. So then I can take one of the days within that 10 to 25-year period after it was built, and I can plot up the differences in velocity vectors, the resupply of oxygen for one day and compare them. So the above one is the conventional mine rock stockpile. The bottom one is building with source control. You can see the larger airflow velocity vector deep within the facility. And this is in a very reactive material. Internal temperature is greater than external temperature. So what's the gas doing? It's coming in from the side, as you can see from the arrows. Exactly the same day, exactly the same rock. No airflow velocity vectors, just a little bit of diffusion and some convective currents that are up. Right? The other cool thing that happens is because sulfide oxidation is an exothermic reaction that generates heat. Well, now I have much less heat generation in the facility. So now I have much less worry about the temperatures inside the facility, which we're taking off, increasing temperature more and more and more. Actually, after the silver mine, the temperatures that I was monitoring when I was a graduate student were like 55, 60 degrees Celsius. There's rock that monitored at the Mount Whaleback mine, the BHP&R in Western Australia. It's a spontaneous combustion self-heating material. They can have temperatures 200, 300, 400 degrees Celsius. So once this thing starts to kick off, and anybody who's worked in the Elk Valley is familiar, you know that there's a bit of a self-heating problem. Right? All kinds of bacteria. It's about gas, thermodynamic ability, and understanding the unsaturated zone system. So an MRS that's built with influence how it performs, mine rock stockpile with a focus on source control represents the highest level, higher risk control, which is manage tomorrow's risk today by building a mine rock stockpile with source control rather than conventional. So all I'm doing is saying, I understand that our mine plans have the constraints of the least cost manner of getting the rock out of the pit onto the ground, putting the rock on the dock. And we also have to make sure they're geotechnically stable. Just changing or environmental protection to an environmental protection. And changing the or to an and just like we do cheapest possible and geotechnical stability, I'm adding an end to that to manage the more risk today. Adding another constraint to the mine plan is say, would you think about it? Amazing things can happen when you change the question, you get a different answer. Just consider it and see if you can actually. So tailings a little bit. For me, it comes down to where's the water tip? Where's the phreatic surface? Where is it now during operations? Where is it going to be in closure? And if you put the right controls in place with confidence, then you're going to take that full water pressure system from today to tomorrow in the right means. Right? And so it always comes back to the same thing. How is it built? What's the water balance? What's the water pressure condition? Where's the water table? Then I'm going to do stream water. So for tailings landforms, where's the water cup? Where's the phreatic surface? If I had a cover system like that one on the left, right? The whole idea behind that cover system is actually to lower the phreatic surface, the net percolation rate. That might help with geotechnical stability for sure. But it also decouples the water table from the interactions with the atmosphere. So I'm not pulling up water and potentially adding salinity to my living zone. So where the water table is phenomenally important, as you guys know. So some thoughts on risk and opportunity. Keeping in mind this context of what I learned from Andy Robinson. How many people were living in Calgary in 2013? Do we all remember the floods? So this is the story behind my flood here along the Elbow River. It was in and around there, and it was amazing, right? So much water. Right? These are the condominium units, the bedrooms, okay? Right there, right? So there's one on the left and the one on the right, the two photos. Can anyone tell me what, just make a wild guess. What do you think is the time frame between the one on the left and the one on the right? Guesses? Would anyone guess 8 years? These condos flooded while they're being built. So in 2005, the exact same. But the maximum foreseeable loss at that time was almost next to nothing. We just got graded. There's no infrastructure down there. There's no HVAC, there's no generators, there's no elevators, nothing like that. So it flooded, big deal. We let it drain, movement back. But it happened in 2013. Everyone was in the building, a bunch of cars got damaged, the entire HVAC system got it. All the elevators, everything. Okay. $30 to $40 million damage paid by insurance. Can you imagine if we learned from this and built up a pony wall instead of a gate, whatever fence here, we actually built it up, put a burn into the background. That would have been a huge savings. Okay. So very often when we're thinking about risk and opportunity, our answers are right there. And this is the thing that Lee Barber was really good at, and Andy Robertson really good at. You couldn't go into a review meeting with them because they read everything that you did. That's why they were so good. They mined the data. And that's the lesson there, is that they would always think about what's the most reasonable expectation. Not what's more likely, always thinking about maximum foreseeable loss, and then come back from it. Rather than trying to say, I've got so much uncertainty, what do I do to reduce the uncertainty? They would go, what's the maximum foreseeable loss? Impose controls, figure out what the risk is, and see if you can actually afford to live with. So if you're not looking peripherally at what could happen, I don't think you're looking wide enough with respect to the risk and opportunity evaluations. So always ask yourself, what could be reasonably expected, as opposed to what you think is most likely, what you can live with, all that sort of stuff. Okay, coming back to where we started. This is me trying to figure out a water balance for the cover system that I did. Trying to figure out the net percolation, the gas transport, the runoff, the evapotranspiration, the similators. I don't even know what the similators. And they just said, well, except but try and start to make things simpler for yourself. Just think about narrowing it down. And in fact, if you really thought about it, you could figure out the water balance for this. How much rainfall and snow water coming in, when the storage is overwhelmed, how much goes through, how much runs over the top. how much of that transpires. And in fact, cover systems are like designing the right size water. That's the lesson from me. You would always bring that forward, design the right size. Keep it as simple as possible, and no simpler to have your complexity captured. So cover systems, designing the right size file. Start off with a really strong conceptualization, and you don't jump to the bottom. You'll get the right model that tells you the story toward conceptualization. And every single one of your conceptualizations, just tell a story about whether or not we have the right size. So, finishing up with land transition. We struggle within the mining industry to think about what's the future when the mines close, right? My perspective is the mining industry is actually really good at understanding the value of future values. Because if they weren't, why would you go and spend money drilling and getting a permit to go do exploration? To do that, we do it because we have an eye on getting to a project description and in the 943-101 to get more investment, to invest more money, to get another permit to do an environmental assessment. And then I want to spend more money, more investment baseline settings to get it to a permitting condition. Then I want to spend more money because I want to get to the next land use, which is construction. I'm going to spend more money because I want to get to operations. And then I'm going to explore more because I know there's uncertainty there. It was a resource, I'm keeping the reserve, and get more drilling while I'm operating so I can do an extension. Right? Doing this all with the eye of knowing that there's some unknown up there and there's some uncertainty, but I'm going to move forward because I have confidence in the future land use and the value. The thread that we're missing as we go to closure is we lose sight of the importance of that future land use. I don't want to make a commitment because what I want. When you weren't worried about that back here, what you did is you did the hard work to go find out so you'd ask more confidence. Right? And the same thing, future land use is that thread across time. Not future land use can be anything. I'm just pulling this from the BC jurisdiction. If I go into 10.7.4 land use, it doesn't say land use has to plant grass or trees. It says land use has to be approved by the chief permitting officer. Every single jurisdiction I've ever come across in the world is exactly similar. It can be anything we want. We just have to actually. In Saskatchewan, when we go to relinquishment, that's starting one of the first models about relinquishment, the institutional control program. But saying, I'm going to monitor for over time, so I have confidence, I understand the maintenance on an annual basis and the unforeseen money funds that could come off. So this site, the Clough Lake site, was moving into Saskatchewan's ICP, which is the control program for relinquishment. It's on its last permit from the federal government licensing. Orano has done an amazing job of over 20 to 25 years of moving it towards this. This one's near and dear to me because this is one of the first cover system landform design. The mine rock stockpile on the bottom and the tailings storage facility at the top. Right, over 20 years, keep the faith, think about the future land use, and we're going to move towards it. So it can be done when you're thinking of the future land use and where you're going to go. And the tools we have are there. Look at the modifying factors to take resources to reserve: legal, environmental, infrastructure, social, economic, and governmental. Those are all about the future, right? So you have somebody who's investing in your property has confidence that you've done it right. So in my mind, the puzzle that's waiting to be solved starts with a vision, right? I've got my life of asset and my NI statement, my LOM, my mine schedule, the resources, my closure plan, my cost models for closure, my basis estimate, LOM, and that missing puzzle piece, when I think about it, is returning land use. That's the piece. In order for me to have confidence with closure plan, I gotta land on returning land use. And where does that returning land use come from? It comes from this vision. I'm thinking that our assets are not liabilities, they're opportunities. How is it possible that an open pit is be an asset for the entire life of mine, even before it's built, and magically it becomes a liability when it's closed? That makes no sense to me. It has to be in this, right? We just need to change our thinking. So a vision for closure is a high-level aspirational description of what an owner, an operator, rights holders, stakeholders and local communities want to achieve. So this is taken right out of the International Council for Mining and Metals, ICMM. What I've done is I've just added rights holders here. Because ICMM considers stakeholders in the community and the indigenous people and rights holders. I've actually taken that out. It's otherwise the same thing. And a vision allows you to actually demonstrate how you're going to achieve that through the implementation of the program. And a vision is where to start. Right? Has anybody been to the Butchart Gardens? Right? So that's a great example. I'll quote directly from their website. It all began with one woman's vision and passion with a former limestone quarry for her backyard. Jenny Butchart envisioned landscaping a sunken garden in its place, transforming the property for her family and visitors for generations. It wouldn't have happened without the vision. I get it. You gotta have a path to, but it starts with a vision. The future land use, the mining industry is that's what allows us to steer it. So begin with the land in mind, not the end in mind. Begin with the land in mind, land stewardship. Think of that thread that takes us through. Literally, the mining life cycle, it's just a snapshot in time. There were people there before, people there after. It's land stewardship, not just land use. So start with a vision that allows us to take closure as an action, not a destination. And when there's disagreement about closure, I guarantee you, it's because you have a different view on vision. You have a different view on future. All right, last thought. I gave you a lot of process time. Process guy. I'm not into the details. I'm just going to give you a little bit of detail of things, right? So process versus outcome, offer some outcome. Accuracy versus precision. If I was to use this INET guidance document, I would tell you, hey, you guys should figure out what the very low, moderate, medium, high, and very high net percolation rates are. It's really important when we conceptualize something to be very accurate about whether I'm here or here or here. High level of confidence. Don't need to be precise in that. I want to be accurate of what range I'm in, but being precise is related. So that's an outcome from the strong conceptualizations of thermodynamics, knowing a lot of equilibrium, and gravity, and they relate to climate. What box am I in on a wide range? And if I start with there and being accurate and confident about that, the design details of the precision that I need within that box, that comes later. That's 30% design, that's 60, that's 90. But if I don't start with strong conceptualization, I'm going to do a bunch of work that's completely out of line with the better action. If you're not thinking that way, then you will forever be in some error. Accuracy versus precision. The classic one is the bullseye, right? I don't want to be precise when I'm shooting at a bullseye and everything lands up over here. My wife's laughing because that's what we shoot. I want to be accurate right around the bullseye and precise. So I hope that makes sense. My perspective on unsaturated soil mechanics and gardening tips. If you like the illustrations, probably see the before Bill's hard work with its compact bills. Just an amazing guy. Such a dead man and a gentleman. Thank you to all of you. It's after hours. I apologize for that, but thank you for the advice. INAP, I did a lot of references to them. I had a good review on this, made it a little better for my colleagues at the team. And thanks to my brother, a good friend of mine, a great mentor. And I'd be remiss if I didn't acknowledge Andrew Robertson about a year ago today. Very lost for the street. And Barlow, who also has to be very well. Lee would say exactly this. He'd always talk about this thermodynamic equilibrium and gravity. Say a great law of energy or mass is the law of science, that conservation of energy or mass. But he'd say in a similar way, great universal law of humanity is no success outside of relationship. So thanks for having me today.